Hello and welcome to the third and final, or maybe fourth and final installment of this series of talks on multivariate models in behavior genetics. I like to start these as ever with dogs. Again, we've got Jamie on the left, we've got Lily on the right, and this time Lily's the pillow. You can tell in their custom handmade sweaters that they live very difficult, strenuous lives. Long day of workshop learning that they just had, so they need to rest up. Getting on to the third installment of this lecture series, so now we're going to be talking about the independent pathways model. So again, we make the same sort of distinction that I mentioned before, talking about the kind of fully correlated genetic factors model that's sort of formally known as the Koleski model versus the more theoretically driven models like a common pathway model or independent pathway model. Here we're talking about the independent pathway model. So place, I like to start with that, talking about the independent pathway model is with the genetic factor model and then adding components to that. So it is a theoretical model. The idea is you sort of start with this biometric factor model. The origin is more biometric than psychometric, and then you allow different covariance structures across the A, C, and E components. You essentially create latent factors for the A component, latent factors for the C component, and latent factors for the E component in the independent pathways model. They're independent sorts of pathways through each of those components. That's sort of the origin. The idea here is, let's say you've got some sort of factor, and you've got one factor, you've got residuals on it, but what do you do if you've got twins here? So essentially what you can do is create an A factor. This matrix here is what I previously notated as L sub A, where you've got a factor loadings component associated with a factor loadings matrix associated with the A component. And then there'd be a different set of factor loadings estimated as separate parameters for the C components and the E component, which we see here. So this one here would be the factor loadings associated with the C component. And then you repeat the same thing for the E component. So now this matrix here would be the factor loadings associated with the E component. These are one factor models associated with the A component, the C component, and the E component. And then you've got a set of residuals that go with that. So again, this independent pathways model is more of this kind of biometric origin where you sort of create separate factors for A, C, and E. And decompose those variants across those more specific components. So this diagram here adds this sort of residual piece where you've got, in addition to the kind of global A, C, and E factors that are sort of common, here it's AC, CC, and EC, you've got specific AC and E factors, and these are basically decomposing the residuals of the factor model that you had before. So if you sort of put the various sort of components of this model together, you end up with kind of mathematically, this gets stated as you've got loadings for A that get multiplied by themselves. Then you've got the loadings for C that get transposed, multiplied by themselves, and the loadings for E that get transposed, multiplied by themselves. And you've got essentially one factor model for A and C and E, and you can see how it grows in this way. So these basically specify the three factors that we have going into the same model. So this component here goes into that A. This component here is what is driving the C, and this component here is what's driving the the E component. In addition to those common bits, you get to add this residual component that again goes with each of those A, C, and E factors. So if we see that next. For readability, we often sort of omit this structure down here, but essentially you end up with this component down here. These three together end up being the what I called before uniquenesses for the A, C, and E components, which are almost always going to be diagonal. The A component is going to be the UA component, the UC component, and the UE component are each going to be diagonal. Where they get related is across members of a family, which in that initial lecture we kind of showed how those get related across a family using the Kronecker product with those relatedness matrices. But for readability in a lot of diagrams, we omit that unique part of the decomposition, which, surprise, leads to some confusion sometimes. But kind of think in your head that even though we aren't showing the E components in here, that those are in there behind the scenes. We talked a little bit before about the dimensions of these matrices, but to see it a little bit, there can be some identification issues associated with this. So when you're adding these factors, the number of free parameters grows very large, the kind of relationships get very large. There's a function that I wrote in OpenMX called MX check identification. So that's one way to check for identification. There are some limitations to that method, but it should give you at least some place to start for a lot of models. To see this sort of model in code, we've got some OpenMX examples here. So this, let's see. So this line here, we are creating the factor loadings for that common. So this part is really creating the L sub A loadings. This part is creating the L sub E loadings. Kind of filling in the idea with the C one. I'll maybe do C over here. So this middle part, path C, that's creating the U sub C set of loadings for this model. And then these things get kind of multiplied out together. So here, the A covariance matrix, that's giving us our L sub A times L sub A transpose. And here it's decomposing this diagonal matrix into elements zone, but it's really just giving you the uniqueness parts in there. So those are the specific factors. And then I think the next slide, it shows how to build those up into a single covariance structure, a single covariance model. Now here we have a diagram of the common pathways model, essentially showing with a large number of behaviors 1 through 7. Here you've got the kind of psychometric factor structures for factor 1, 2, and 3, and you've got ACE decompositions on those factors. So again, with that feature of this common pathway model, which we talked about before, is you've got psychometric factors and you've got kind of biometric decompositions on each of those factors. Now in the independent pathways model, so this is you can view that as sort of a special case here, where you've got a special kind of factor structure. So if we kind of go back, essentially you've sort of put the biometrics kind of in with the psychometrics and sort of merge them in with the independent pathway model. And you can see how these models then get nested. You've got a 3-factor common pathway model with sort of very specific structures on top of it. So the independent pathway model is nested within the three-factor common pathway model. Again, the point here, just to return to it, is with univariate analyses, we typically just want to decompose variance into its various components. With the multivariate analysis, we want to structure and model the covariance. And some common ways of doing that would be, say, a genetic factor model, independent pathways model, common pathway model, as three kind of examples. But really, the sky's the limit. Any model that you want to fit to those is something that's worth considering, I think. Okay, I think that's it for now.